I believe you've written Drake.
There's a team of people. I certainly spent a lot of hours on it myself.
Well, what is Drake, and what does it take to create a simulation environment for the kind of difficult control problems we're talking about?
Right. So Drake is the simulator that I've been working on. There are other good simulators out there. I don't like to think of Drake as just a simulator because we write our controllers in Drake, we write our perception systems a little bit in Drake, but we write all of our low level control and even planning and optimization in
So it
Drake.
has optimization capabilities as well.
Absolutely, yeah. I mean, Drake is three things roughly. It's an optimization library, which is sits on it. It provides a layer of abstraction in C++ and Python for commercial solvers. You can write linear programs, quadratic programs, semi-definite programs, sums of squares programs, the ones we've used, mixed integer programs, and it will do the work to curate those and send them to whatever the right solver is, for instance, and it provides a level of abstraction. The second thing is a system modeling language, a bit like LabVIEW or Simulink, where you can make block diagrams out of complex systems. Or it's like ROS in that sense, where you might have lots of ROS nodes that are each doing some part of your system. But to contrast it with ROS, we try to write, if you write a Drake system, then you have to, it asks you to describe a little bit more about the system. If you have any state, for instance, in the system, any variables that are going to persist, you have to declare them. Parameters can be declared and the like. But the advantage of doing that is that you can, if you like, run things all on one process, but you can also do control design against it. You can do, simple things like rewinding and playing back your simulations. For instance, these things, you get some rewards for spending a little bit more upfront cost in describing each system. And I was inspired to do that because I think the complexity of Atlas, for instance, is just so great. And I think Ross has been incredible, absolute huge fan of what it's done for the robotics community. But the ability to rapidly put different pieces together and have a functioning thing is very good. But I do think that it's hard to think clearly about a bag of disparate parts, Mr. Potato Head kind of software stack. And if you can, ask a little bit more out of each of those parts, then you can understand the way they work better. You can try to verify them and the like, or you can do learning against them. And then one of those systems, the last thing, I said the first two things that Drake is, but the last thing is that there is a set of multi-body equations, rigid body equations, that is trying to provide a system that simulates physics. And that we also have renderers and other things, but I think the physics component of Drake is special in the sense that we have done excessive amount of engineering to make sure that we've written the equations correctly. Every possible tumbling satellite or spinning top or anything that we could possibly write as a test is tested. We are making some, I think, fundamental improvements on the way you simulate contact.
Yeah, so what does it take to simulate contact? It just seems there's something just beautiful the way you were like explaining contact and you're like tapping your fingers on the table while you're doing it, just
Easily, right?
Easily, just not even like it was like helping you think, I guess. What so you have this like awesome demo of loading or unloading a dishwasher, just picking up a plate, grasping it like for the first time. That just seems like so difficult. How do you simulate any of that?
So it was really interesting that what happened was that we started getting more professional about our software development during the DARPA Robotics Challenge. I learned the value of software engineering and how to bridle complexity. I guess that's what I want to somehow fight against and bring some of the clear thinking of controls into these complex systems we're building for robots. shortly after the DARPA Robotics Challenge, Toyota opened a research institute, TRI, Toyota Research Institute. They put one of there's 3 locations. One of them is just down the street from MIT, and I helped ramp that up right out as a part of my the end of my sabbatical, I guess. So TRI has given me the TRI robotics effort, has made this investment in simulation in Drake, and Michael Sherman leads a team there of just absolutely top-notch dynamics experts that are trying to write those simulators that can pick up the dishes. And there's also a team working on manipulation there that is taking problems like loading the dishwasher, and we're using that to study these really hard corner cases kind of problems in manipulation. So for me, this, simulating the dishes, we could actually write a controller. If we just cared about picking up dishes in the sink once, we could write a controller without any simulation whatsoever, and we could call it done. But we want to understand, like, what is the path you take to actually get to a robot that could perform that for any dish in anybody's kitchen with enough confidence that it could be a commercial product, right? And it has deep learning perception in the loop. It has complex dynamics in the loop. It has controller. It has a planner. And how do you take all of that complexity and put it through this engineering discipline and verification and validation process to actually get enough confidence to deploy? I mean, the DARPA challenge made me realize that that's not something you throw over the fence and hope that somebody will harden it for you, that there are really fundamental challenges in closing that last gap.
They're doing the validation and the testing.
I think it might even change the way we have to think about the way we write systems. What happens if you have the robot running lots of tests, and it screws up, it breaks a dish, right? How do you capture that? I said you can't run the same simulation or the same experiment twice on a real robot. Do we have to be able to bring that one-off failure back into simulation in order to change our controllers, study it, make sure it won't happen again? Is it enough to just try to add that to our distribution and understand that on average, we're going to cover that situation again? There's like really subtle questions at the corner cases that I think we don't yet have satisfying answers for.
Like, how do you find the corner cases? That's one kind of. Do you think it's possible to create a systematized way of discovering corner cases efficiently?
Yes.
In whatever the problem is?
Yes. I mean, I think we have to get better at that. I mean, control theory has, for decades, talked about active experiment design.
What's that?
So people call it curiosity these days. It's roughly this idea of trying to exploration or exploitation, but in the active experiment design is more specific. You could try to understand the uncertainty in your system, design the experiment that will provide the maximum information to reduce that uncertainty. If there's a parameter you want to learn about, what is the optimal trajectory I could execute to learn about that parameter, for instance? Scaling that up to something that has a deep network in the loop and a planning in the loop is tough. We've done some work on, with Matt O'Kelly and Amancina, we've worked on some falsification algorithms that are trying to do rare event simulation that try to just hammer on your simulator. And if your simulator is good enough, you can spend a lot of time, or you can write good algorithms that try to spend most of their time in the corner cases. So you basically imagine you're building an autonomous car and you want to put it in, downtown New Delhi all the time, right? Accelerated testing. If you can write sampling strategies which figure out where your controller is performing badly in simulation and start generating lots of examples around that, it's just the space of possible places where things can go wrong is very big. So it's hard to write those algorithms.
Yeah, rare event simulation is just like a really compelling notion, if it's possible.
We joked and we call it the black swan generator,
It's a black swan,
right? Because you don't just want the rare events, you want the ones that are highly impactful.
I mean, those are the most sort of profound questions we ask of our world. Like, what's the worst that can happen? But what we're really asking isn't some kind of like computer science worst case analysis. We're asking like, what are the millions of ways this can go wrong? And that's like our curiosity. We humans, I think, are pretty bad at, we just like run into it. And I think there's a distributed sense because there's now like 7.5 billion of us. And so there's a lot of them, and then a lot of them write blog posts about the stupid thing they've done. So we learn in a distributed way. There's
I
some,
think that's going to be important for robots too.
yeah.
I mean, that's another massive theme at Toyota Research for robotics is this fleet learning concept. Is the idea that I, as a humanoid, don't have enough time to visit all of my states. Right? It's very hard for one robot to experience all the things. But that's not actually the problem we have to solve, right? We're going to have fleets of robots that can have very similar appendages. And at some point, maybe collectively, they have enough data that their computational processes should be set up differently than ours, right?
I have this vision of just, I mean, all these dishwasher unloading robots. I mean, that robot dropping a plate and a human looking at the robot, probably pissed off.
Yeah.
But that's a special moment to record. I think one thing in terms of fleet learning, and I've seen that because I've talked to a lot of folks, just like Tesla users or Tesla drivers. They're another company that's using this kind of fleet learning idea. And one hopeful thing I have about humans is they really enjoy when a system improves, learns. So they enjoy fleet learning, and they're the reason it's hopeful for me is they're willing to put up with something that's kind of dumb right now, and they're like, if it's improving, they almost like enjoy being part of the like teaching it. Almost like if you have kids, like you're teaching them something,
right?
And, I think that's a beautiful thing because that gives me hope that we can put dumb robots out there. The problem with on the Tesla side with cars can kill you. That makes the problem so much harder. Dishwasher unloading is a little safe. That's why home robotics is really exciting.